Figure 6 shows a sketch of the curve C with parametric equations given by x equals 8 sine squared t and y equals 2 sine 2t plus 3 sine t, and we're told that t is between 0 and pi by 2. The region R, shown shaded in figure 6, is bounded by the curve C, the x-axis, and the line with equation x equals 4, and we can see all of that in the diagram. We want to show that the area of R is given by the integral from 0 to a of 8 minus 8 cos 4t plus 48 sine squared t cos t dt, where a is a constant to be found. And then in part B, we're going to integrate to find the exact area. Bulk of the work here is in part A. So, we know that the area is the integral of y dx, in this case between x is equal to 0 and x is equal to 4. But we can replace y with 2 sine 2t plus 3 sine t. So we have 2 sine 2t plus 3 sine t. And then dx can be replaced by dx dt dt. Now let's think about the limits. We know that x is equal to 8 sine squared t. Remember that means 8 sine t squared. So if we differentiate that, the 2 comes down in front and multiplies the 8. We then have sine t, and then by the chain rule, we have to multiply by the differential of the inside function. So that gives us cos t. So we can now write that a is equal to the integral of 2 sine 2t plus 3 sine t multiplied by 16 sine t cos t dt. And let's deal with those limits now as well. We know that x is equal to 8 sine squared t. The bottom limit is x is 0, and that would work if t was equal to 0, since sine t is equal to 0. So x is 0 means t is 0. And that matches with the 0 that we have on the bottom down here. What we need to do is find the other limit. So x is equal to 4 is our other limit. So that's going to give us that 8 sine squared t is equal to 4. That means sine squared t is equal to 1/2. Sine t is equal to 1 over root 2. Note the restriction on t, so it can't be anything else. And then that would give us that t is equal to pi by 4. So the top limit is pi by 4. And so we can state that the constant a is pi by 4 at this stage. Okay, so expanding this out, we get the integral from 0 to pi by 4 of 32 sine 2t times sine t times cos t, and then we have 48 sine squared t cos t dt. Note that the second part of this is what we want in our target expression just here. So that part has already been done, but we're going to need to get to this, and that's quite a bit of work. The first thing to note here is that sine 2t is 2 sine t cos t. So if we change this sine 2t into 2 sine t cos t, remember we're multiplying by sine t cos t here, then what we have is 64 sine squared t cos squared t plus the 48 sine squared t cos t, which we already have, and it's what we want. So we need to work further with this first term. So let's have a quick look at that term and what we've got to come from that. 8 take away 8 cos 4t. So that's giving us some ideas as to what to do here. Remember that cos 2t is equal to 2 cos squared t take away 1. It's also equal to 1 minus 2 sine squared t. So from there, sine squared t can be replaced with the following. So sine squared t can be replaced by 1 minus cos 2t, all divided by 2. And that is just a rearrangement of that being equal to that. Then we have the cos squared t, and we can see that the 1 goes over here, cos 2t plus 1 divided by 2. So that's going to be 1 plus cos 2t divided by 2. And then we've got the 48 sine squared t cos t dt. So integral 0 to pi by 4. Now the 2 and the 2 here cancel down with the 64 to give us 16. 64 divided by 4 is 16. And what we have left with these two brackets is a difference of perfect squares. So we can write that as 1 minus cos squared 2t. And then we've got plus 4 sine squared t cos t. So it's 48, isn't it? I lost the 8 at the last line. And there we go. Okay, so the 1 minus cos squared t, we're going to go back to the cos 2t expression. If we just double the angles there, and that's 4t, then this here would end up being 2t. And so we would get cos 4t plus 1 divided by 2. So that's going to be the integral from 0 to pi by 4 of 16, 1 take away 1 plus cos 4t divided by 2, and then plus the 48 sine squared t cos t dt. And so note what we're going to get here. It's going to end up being 1 take away a half, take away cos 4t over 2. So we have 16, a half, take away cos 4t divided by 2, plus 48 sine squared t cos t dt. And expanding that out is going to give us the integral from 0 to pi by 4 of 8 take away 8 cos 4t plus 48 sine squared t cos t dt, which is what we were trying to show. So now for part B, where we actually want to evaluate this integral. So that is going to be 8t. Cos integrates to sine, so we have minus 8 sine 4t. Don't forget to reverse chain. We need to divide by the differential of the inside function, which is 4. And then for this one here, we have an integral of the form integral of sine to the nt cos t dt. And when we do that, it's going to be sine n plus 1 t divided by n plus 1. So in this case, we're going to get 48 sine cubed t divided by 3. And that's going to be evaluated from 0 to pi by 4. So that is the 8t. Take away 2 sine 4t plus 16 sine cubed t from 0 to pi by 4. Now note the bottom limit of 0 is just going to give us 0 for all three of those terms. So we're only needing to worry about what happens with the pi by 4. So that is going to give us 8 pi by 4. Now 4 pi by 4 is pi, so that's going to be take away 2 sine pi. Sine pi is 0, so this part is going to disappear. And then we have 16 sine cubed pi by 4. So that's going to be 2 pi. And then we have 16 sine of pi by 4 cubed. So that's 2 pi plus 16 times 1 over root 2 cubed, which is 2 pi plus 16 over 2 root 2. So that's going to cancel down to 8. And then that would be 8 root 2 over root 2 times root 2. So it's going to be 4 root 2. So 2 pi plus 4 root 2 square units.